We have Lohann, who will be speaking about how to build an optimized and economically secure parachain. Lohann?
Sure, thank you very much, Bill. So nice to meet you guys. I'm Lohann, blockchain engineer at Enjin, and today I would like to talk very briefly about our experience building the Efinity Parachain. But before talking about Efinity, I would like to very briefly introduce Enjin and why we have decided to build the Efinity Parachain. Enjin is a company that exists since 2009 and have a lot of experience in the blockchain, NFT, and gaming background. Our CTO, Vitek Handomsky, is the one who proposed and drafted the ERC 1155 standard. And also, I will talk about the ERC 1155 very briefly, but also Enjin have made lots of contributions in the blockchain ecosystem, creating things like wallets, SDKs that make very easy for other game developers or third-party companies integrating their ecosystem with the blockchain. So now let's talk about the ERC-1155 standard. For who doesn't know, the ERC-1155 is a multi-token standard built for the Ethereum network. It reduces a lot the transaction fees, and it's basically allow us to implement both fungible tokens and non-fungible tokens under the same spec. And regarding to that, now talking about Efinity. Efinity is a parachain that has been built to be the best in class for trading and make NFTs. Basically, the goal is to turn NFTs and trading assets far more accessible than what we have right now. We want to basically create allow batch operations, reduce a lot the fees, and create the best-in-class blockchain for NFTs. That's the goal of Efinity, in short. So our team, we select some topics that I would like to share with you guys, things that we learned when we have built that parachain. So the first one, I would like to talk about how we prevent economic attacks and what are economic attacks, how we keep the storage clean and compact, and some optimizations that we did in our parachain. So first, let's talk about how we prevent economic attacks and what are economic attacks. So there are two kinds of economic attacks. For example, DDoS attacks that we can, for example, shut down nodes by sending a lot of transactions with low costs, for example, or even state bloating. To explain what's that, basically economic attack is when the costs of process operation, for example, a transaction, is is actually high than the costs of send a transaction. Let's say that a node to process a transaction spend $1, but the cost in fees that you pay for the transactions is 10 cents, for example. A malicious user can exploit that and start to increase the storage. So just to provide more context on that, let's see some real example of economic attacks. So in this graph, you can see a list of Ethereum hard forks. And there's two that I would like to point out, the Tangerine Whistle and the Spears Dragon. The Tangerine Whistle was a hard fork that fixes the fees for storage operations, read and write storage. The cost was too low, and basically there's people start to write some smart contracts operation that exploit this behavior and start to spend a lot of IO operations, which slow down the network a lot and shut down some nodes. So it was the Tangerine Whistle, and like 1 or 2 months after that, they also released the Spiral Dragons that basically clean up the storage because it was too cheap to create accounts and basically store data in Ethereum. So it was a hard fork that they made to fix that. And another example is UTXO in Bitcoin. In this graph, you can see that the growth of UTXO in Bitcoin. And a lot of those UTXO are not actually, it's not because of the popularity of Bitcoin. Some of them are related to that, but some of them is what we call dust. It's basically is a very, very tiny amount of Bitcoin that are allocated in some UTXOs, and basically the nodes need to keep that in memory. That blows the states and require more resources from the nodes to process and run a full node of Bitcoin. So, and in that graphic, we can see, for example, in the blue line, we can see the number of accounts in Ethereum from the entire period for the last 5 years, I think. And in the black line, we can see the average of Ether per account. So we can see that actually the number of accounts have been increased, but the number of Ether per account has decreased. And again, that consumes a lot of resources from the nodes. Basically, the developers from the nodes have to create a lot of clever stuff to mitigate that that does not use a lot of memory for storing this kind of data. And in Substrate, as you guys know, one way that Polkadot and the asset balance provide to mitigate that is providing the existential deposit, where the account needs to have a minimum amount of tokens in order to exist. So this is a way for preventing this kind of attack. But there's also other attack vectors. For example, let's say that you create asset storage. You create something that store data in your blockchain. It's not, you also need to worry about if you are increase the storage size, that thing you need to charge the fees for that. Otherwise, it will become a attack vector. So one way that Substrate provides to us to deal with that is the way that, for example, the assets and the uniques palette deal with that is a config where you can define the base deposit and deposit per byte. The base deposit is basically an amount of tokens that you need to allocate in order to create a new asset. And the deposit per byte, let's say that you want to store some metadata in your token, is a fee based on the amount of data that you want to store in your palette. Those parameters are very important because it's a way to prevent economic attacks in your chain. Because if your chain starts to grow indefinitely, the nodes will require more memory, require more resource, and people will basically stop working. You can basically stop working your chain completely if you don't take care about that. Now I will talk very briefly about the storage cleanup. You need to charge the fees for storing data, but you also need to clean this data. Let's see, that is more tricky than it sounds. Let's see why. So in this example here, I have two storage. One that we basically keep the assets, and we have the attributes associated to this asset in the second one. So basically, you can think like we have a table of assets and another one with the attributes associated with that asset. The trick thing is when we need to delete an asset, for example. In this case, that's a very bad way to do that. When you destroy an asset, you basically remove that, and you remove all attributes associated with this asset, and you do not take account how many attributes you have per asset. Remember that this an attribute is a mapping, so you can have like 1 billion attributes associated with this asset. And if you don't take care about that, and if you don't charge the correct fees for that, basically one transaction like that can block your blockchain because it's going to use more weight from a block than a regular transaction. So a better way to do that, for example, the most simple solution is, for example, charging the worst case scenario. So let's say that you can have up to 20 tokens per asset. So you always charge 20 storage reads from the user. You can see the parameter in the extrinsic decorator there. And you reimburse the user. Let's say that it was only 10 attributes. You can reimburse the user from the, you charge 20, but you can reimburse the other 10 that he does not delete, for example. But the bad thing about that is that we always charge the worst case scenario. So let's say that you want to allow like millions of attributes for this token. So that's not a good solution for that. Another one, that's the one that I think that Parity Unix is using, is providing what we call a extrinsic witness. So basically, when you send a transaction to delete a token or do some storage operation that we need to clean up your storage, you can provide, for example, a tip of how many tokens you have associated with this attribute. This solution is good because you charge the exact amount of tokens that the user have, but have some downsides of that. The user who call this extrinsic needs to know how many attributes are associated with this asset. And if for some reason it's out of sync, you can see in that ensure statement, this transaction is going to fail. So if for example, the user said, okay, have 10 attributes, but when your transaction is processed by the node, that amount changes, the transaction is going to fail in that case. So this, for example, is only advised if the attribute, for example, count does not change a lot. So this is one way to mitigate that. And the other complication that have associated with that is the smart contract integration, because smart contract needs to know the state of the token, how many tokens, how many attributes it have, in order to delete that. Another solution for that is lazy deletion. That's the approach adopted by the smart contracts repo. In this approach, for example, you delete a token and you put that in a pending pool. So for example, there's a new feature for Substrate where you can use on idle hooks for cleanup this data. So the good thing about that is that you always have a constant weight price for cleanup the storage using this approach. So in one block, you delete the asset, and only if there is some remain weight in a block, it's going to delete the data. And last but not less important, we also can have some economic incentivizes for cleanup the storage. This is a good example of that is also the smart contracts. If the user don't pay a rent, or there is a lot of pending contracts that need to be deleted, basically you have a string that you can call to delete this contract. But instead of paying for that transaction, you are actually be rewarded for that. So if you successfully delete the contract, you are getting rewarded for that. So you can use that approach also. Let's talk about the optimizations that we did in our parachain. One of the biggest issues that other blockchains are facing right now are the very high cost of fees for manipulate NFTs. Vitalik even suggests moving all NFTs to layer 2 in order to deal with that. One of the guilds for the very high cost of transaction fees in Ethereum right now are NFTs. I checked that today, and it's up for doing a simple transfer of ERC 721 token. It's about $20. So it's not very accessible. We cannot make NFTs mainstream with those very high transaction fees. But let's see why it's so expensive to manipulate NFTs in Ethereum and in other blockchains. So very briefly, the way that Substrate and other blockchains represent the data internally, they use a data structure called Basis 16 Modifier Merkle 3 or Merkle Patricia 3. In this example, we can see the structure from Ethereum specifically. Polkadot have a slight different structure. They don't have extension nodes, only branch and branch extension and leaf nodes. But that's how Merkle tree looks like. But a simplified version of that is that one here. So this, for example, is how the Parity Unix represent data. So we have a path in that Merkle tree that represents the asset. And we have at the end of each node, we have who is the owner of that NFT. So in that example, let's look at the first NFT there. So for example, the NFT 0x97B96B07A. That's the NFT ID, for example. The owner is Bob in that example. When we transfer that NFT, we actually need to update all those nodes in order to change the owner of that NFT. And that's even worse when you need to do, for example, a batch transfer. Let's see that John wants to transfer all its NFT to Fred, for example. In that case, it needs to update a lot of nodes, and each one of them, it means that we need to read the storage, update the owner, calculate the hash of each one of those nodes. And that's really expensive, computational expensive. And in Efinity, we want the ability to mint not 100, we want to mint millions of tokens at once. We want to transfer billions of tokens at once. So using that structure, that's not possible. And just for example, the real Merkle tree structure that have millions and millions of tokens will look more like that. It's actually, there's a way to fit millions of tokens here. So this approach does not scale. So one thing that we did in Efinity for optimize that, and is one thing that Substrate allows us to do, is optimize, change the way that we actually store this data. So instead of storing one owner, one NFT per node in that Merkle Patrizia tree, we are actually doing what we call a chunk. We can compress like 100,000 NFTs in one node. So when we upgrade that node, basically we can manipulate 1,000 NFTs with just one storage write and one storage read. And another thing that we are doing, instead of the blockchain is asynchronous. A single blockchain works synchronously. So instead of allowing the user to provide, for example, I want to make the NFT with that number, we have a sequence number. So these things basically allow us to, for example, mint millions of NFTs in a single transaction. That is not possible in Ethereum. That's not possible in any other blockchain. So just to show you guys some benchmarks in comparison, the base implementation that was inspired in Parity Unix, we can see in the first graph how many weight we use for the first implementation. For example, we can even see the graph after the storage optimization, because it was like 5,000, using like 5,000 less weight than the common implementation. And same for batch transfer and single NFT transfer. The only downside, we have a little degradation performance for single transfers, but the benefits of mint many NFTs at once and transfer that then in batch basically suppress those drawbacks. So yeah, it's pretty much that, and let's open to questions. Thank you very much.
All right. Yes. Thank you. Thank you very much, Lohann. There's a couple of questions that we had here. I'm especially curious. You had mentioned wanting to handle, very large numbers, millions of NFTs, and I know this question is probably going to come with a lot of caveats. And but do you have any estimates on how many you can handle, theoretically on your chain? Like how many NFT transfers in a given amount of time, or?
We don't have this number because, for example, right now the block weight for parachains are coupled by 50 milliseconds, and we actually need. It depends a lot of. There's a lot of variables on that. In your benchmark tests, using the tools that Sub0 provide to us, we only have a direct comparison, and we achieve like 50,000 improvement for that. It means that using the
Oh,
same
wow.
transaction, we can improve like 50,000 more NFTs using the same weight. We have that in our website if you guys want to see details how we did that.
Okay, yeah. Yeah, I definitely would be interested in looking into that. And so getting back to the earlier part of your talk, and the economic attacks against chains. And, we know they're very common. I'm curious, do you have any thoughts on how important or how prevalent those are compared to other, perhaps more traditional attacks?
The problem with economic attacks is that people usually only worry about them when they happen. So, and when they happen, it's a pain. As for example, Ethereum had to do 2 hard forks, emergency hard forks, in order to fix that. So I think that it's better to you charge a high fee, thinking the worst case, and decrease the fees if you find out a way to solve that in the future. So yeah, that's my tip. Don't prevent economic attacks before they happen, because when they happen, it's terrible.
Yeah. Yeah. And I guess, yeah, very unexpected and often like black swan like to determine. All right, well, thank you very much for a very interesting talk.